Yeah, thanks for joining. I'm David. I work as a software engineer at VMware for 4 years in the RabbitMQ team. And this talk is going to be about MQTT. So this is the agenda. We first give a very short introduction of what MQTT is. Not everyone might be aware. Many people have heard of it, but maybe don't understand why it actually exists. Then we talk about Native MQTT, which shipped in 3.12, and then about MQTT 5, which will ship in 3.13. So let's start with why MQTT actually exists. So it's a messaging protocol for the Internet of Things. And for example, use cases would be a car sharing service where data is collected from a vehicle, or where you execute remote commands on the car to lock or unlock the car. And while MQTT is written for Internet of Things, AMQP is more like for business messaging, so microservices. But you could also use AMQP for IoT in certain scenarios. So in MQTT, everything is topic-oriented. So clients publish to topics and subscribe to topics. The protocol is designed to be very lightweight. So you have small message headers, and it provides fast connection establishment. And that's great for unreliable cellular networks. So imagine you have a device where you have lots of network glitches, so you need to reconnect fast to the MQTT broker. And just to illustrate the last point, to give you an idea of how the MQTT protocol is designed, if we compare connection establishment to other messaging protocols, then we see that in AMQP 091, this is the connection establishment. So there's a lot of back and forth going on between client and server. And even the AMQP 091 spec states that the connection is designed to be long-lasting. This is connection establishment in AMQP 1.0. Again, lots of back and forth going on. But this is the synchronous version. You can also do pipelining. So for example, the client could send the begin session. Mike is here. So the begin session frame before it receives the connection open frame, so you can do some form of pipelining. But just to compare it against MQTT, in MQTT, you connect, get back a packet, and then you send your first published packet already out. And even here you can do pipelining, so you can send your published packet before you get your connection. So it's just to give an idea of how the MQTT protocol is designed: lightweight and fast connection establishment. MQTT is not only lightweight, it's also simple and easy to implement. And that's a very important characteristics. So it's simpler than AMQP, although less powerful in features. But this simplicity allowed a huge ecosystem of MQTT clients, brokers, and tools and UIs and so on. So there are some brokers out there, for example, EMQX, which is written in Erlang, good MQTT broker. WernerMQ is written in Erlang. And Mosquito and HiveMQ, you already have heard of them probably as well. Right, so before we jump directly into native MQTT, we first need to understand RabbitMQ a bit better in terms of how it's implemented and how its core model works. So originally, RabbitMQ implements the AMQP 091 protocol. But the 091 protocol is special. So the first thing it defines is the interaction between client and server. So that's what's called in the spec the Advanced Message Queuing Protocol, so AMQP. And it's special because it not only defines the interaction between client and server, it also defines server semantics. So the protocol defines that there should be, or that there must be exchanges, queues, bindings, virtual hosts, and these kinds of things. And this is very special because none of the other messaging protocols define the server semantics. So MQTT, STOMP, or AMQP 1.0 only define the interaction between client and server, not the server semantics. So, for example, the MQTT spec doesn't define how a broker implements subscriptions and topic routing, or whether the MQTT broker uses a queue or a lock, or, I don't know, a SQL database to store the messages. It's not defined. And similarly for AMQP 1.0, you have like destination addresses, or source addresses, but how the addresses look like, this is broker specific. So in the following slides, I will refer to the AMQ 091 model very often, and this is part of the 091 spec, but this does not refer to the protocol, so that's important to understand. Now, if we look at the AMQ 091 model, we have the queue that stores messages, we have bindings that relays queues to exchanges, providing some message routing criteria, and then the AMQ model abstraction is all about a message is being sent to an exchange, and exchanges do then intermediate filtering and inspection of messages that's hidden from the sender, and they route messages to queues, which is also hidden from the sender. And the AMQP 091 spec even defines different exchange types. So there are mandatory exchange types, and RabbitMQ has lots of custom exchange types. And it happens that there's one exchange type, which is the topic exchange. And that's great because we know MQTT is topic-oriented, so we can just reuse that exchange type. The only difference is the character sets being used. So an MQTT topic has multiple words, so it has a hierarchical structure, and every word is separated by a topic level separator. So in MQTT is the slash, in AMQP 091 is the dot sign. And then there's some other characters for single level wildcard, multi-level wildcard. So for example, to match 0 or more words, in both specs it's the hash character. So to give an example, we can publish to RabbitMQ with MQTT and then consume with another protocol, so with AMQP 091. And this works because we publish the message with, for example, in this case, topic is sport/tennis/player1. And then the MQTT plugin in RabbitMQ just translates the topic to the AMQ format. So sport.tennis.player1. And if a queue happens to bind with a matching binding key, in this case it does, because the hash sign matches multiple characters, then the message gets into the queue and then being consumed by the consumer. So we just saw on the previous slide that MQTT topics are routed via AMQ 091 topic exchanges. And also we can implement MQTT subscriptions as AMQ 091 queues and bindings, because they just store the messages, and the bindings are the topic filters in MQTT. So matching topics and then receiving messages. And this means that just this small subset of RabbitMQ's AMQ 091 core model provides already more than half, more or less, of an MQTT broker implementation. And if you think about it, this shows just how powerful and flexible the AMQ 091 model is and how it allows cross-protocol interoperability. And the rest is then just implemented in RabbitMQ's MQTT plugin. And the rest is parsing and serializing of MQTT packets, translating across MQTT and AMQ topics, and a bit more like MQTT-specific features, for example, storing retained messages and sending of will messages. Right, so this is RabbitMQ before native MQTT was supported. So this is up to 3.11. And the picture looks a bit complicated and heavy, and this is also how the implementation was. So every blue dot P here is for an Erlang process. And previously, so up to 3.11, MQTT traffic was proxied internally within RabbitMQ via the AMQ 091 protocol. So this means we needed an AMQP 091 client, which sits in the MQTT plugin, and a server, which sits in the Rabbit core Erlang application. And this happened for every incoming MQTT connection. And not only that, you needed connection process, so AMQ connection process. You needed a channel process on both sides, but not only one channel process, you needed two, because one for quality of service 0 level in MQTT, which is at most 1 semantics, another one for quality of service 1, at least 1 semantics, a few supervisors on top, then a few heartbeat processes on top. So you ended up with 22 Erlang processes per incoming MQTT connection. And we know like Erlang processes are cheap, you can create many, you can create them fast, destroy them fast. However, if you want to support like 1 million MQTT connections, and this is really what the use case about MQTT is about, so you need, for example, support 1 million cars which connect to your single MQTT broker, then we ended up with 22 million Erlang processes, which doesn't scale well, at least. Yeah. So with native MQTT, we end up with a single Erlang process per incoming MQTT connection. And the most important part is that MQTT is not proxied anymore via the AMQ 091 protocol. However, we still use the AMQ 091 model internally, so that's very important to understand. So we still use topic exchanges and queues, and both is great. So it's great that we do not proxy anymore via the AMQP 091 protocol, because this means now we get higher throughput, lower latency because of less message hops, and also MQTT is not constrained anymore by the subset of AMQP 091 features it provides. And it's also great that we still use the AMQ 091 model, because as shown previously, this is what really powers RabbitMQ. So it provides the flexibility and cross-protocol interoperability of RabbitMQ. Now this scales better. We have a single for 1 million MQTT connections, we end up now with 1 million Erlang processes. And we still get parallelism despite having only one process, because as more and more clients connect, we keep the CPUs busy, which is what we want. So this is memory comparison of MQTT in 3.11 versus native MQTT in 3.12. And here we connect 1 million clients to RabbitMQ. So on the very left, we have 0 clients, and then on the very right, we have 1 million clients. And the 3 lines in red, this is a 3-node RabbitMQ cluster in 3.11, and the green lines are a 3-node RabbitMQ cluster in native MQTT in 3.12. And we see that if you sum up the numbers, we require around 300 gigabyte just to connect 1 million MQTT connections in 3.11, but only 18 or 19 gigabyte in 3.12. So this is a huge memory saving. In this test, we switch off management matrix and also use very small TCP buffer sizes. So this is probably not, the performance gain you will see in production. I wouldn't say the test is artificial, but the goal of this test was to really just compare native MQTT in 3.12 versus 3.11. This is another test, 200,000 connections, so 100K publishers, 100K consumers, which send messages to each other in a one-to-one topology, and again, 8 times less memory usage in 3.12. We also have higher throughput with native MQTT. So in this benchmark uses 100 MQTT client pairs, so they send in a one-to-one topology. So there are 200 clients in total, so 100 publishers, 100 subscribers. And each publisher sends 10,000 messages to a single subscriber. And all clients run concurrently, but the messages are sent synchronously. So a publisher sends a message, waits until it gets the pub arg packet, so the acknowledgement or publisher confirm back from the broker, and then sends the next one. And subscribing clients also acknowledge every packet. And in this case, with native MQTT, we have 36% higher throughput. And that's, again, because we omit this proxying via AMQP 091, so we don't need the message hops anymore via the AMQ connection process, channel process on the client side, channel process on the server side, and then on the way out. So we just omit this additional hop. This is the same benchmark, but just comparing latency. So this is end-to-end latency between the point in time the client publishes the message and the subscriber consumes the message. And again here, much lower latency, 57%. And I think we are very proud of this, because for the first time ever, we were able to really connect millions of clients to RabbitMQ. So we showed that RabbitMQ can scale with many clients. So we had one development environment where we connected 9 million clients to RabbitMQ. And this resulted in 56 gigabyte memory usage per node in a 3-node cluster, which is, I would say, decent for that amount of connections. So we have huge memory savings, and it's not only because we have a single Erlang process, because we also made this single Erlang process as lightweight as possible. And we have higher throughput and lower latency because we omitted the proxying. Now this is a slide from last year's RabbitMQ Summit in London. And this was a talk about RabbitMQ performance improvements. And this was about how the queue often becomes a bottleneck compared to the AMQ connection process or channel process. And this is because the queue does the heavy work and writes the messages to disk, needs to replicate. And then there were a few solutions like don't use a single queue, spread your workload over multiple queues. Use new queue types which are faster. And then there was one item, or don't use any queue at all, which is interesting because RabbitMQ is all about queuing, right? You need to store your message somewhere. But we implemented this last approach, so no queue at all, as an optimization for MQTT. But only in the special case where an MQTT client connects with clean session equals 1, or session expiry interval set to 0 in MQTT5, and subscribes with quality of service 0, so at most 1 semantics. So this means clean session equals 1 means that as soon as the client disconnects, the session is gone and any session state, including any messages for the client, are deleted. And quality of service 0 means messages might get lost. So I said we skipped the queue type, but it's still implemented so we skipped the queue process, but it's still implemented as a queue type. So there's still a queue record in RabbitMQ's database in Amnesia or in Future and Capri. And this is in order to route messages, so just internal way of easier message routing, so that you can still, for example, send messages from other protocols, AMQP 1.0, for example, and route it to this new queue type. It's hidden behind a feature flag. It's called RabbitMQTT QS0 queue. And if it's inactive, so this is how it behaved up to RabbitMQ 3.11. We create a classic queue by default for an MQTT subscriber. So a classic queue has its own supervisor process, which is very lightweight. But nevertheless, if you have 1 million subscribing MQTT clients, you ended up with 3 million Erlang processes. So if the feature flag is active, we just skip the queue. So there's no separate queue process anymore. Messages are not written to disk. And basically, you can think of the queue being a subset of the Erlang process mailbox of the receiving MQTT connection process. And this comes with a large number of benefits. So first of all, and this was the main reason we implemented it, it allows for larger fan-outs, so sending a single message from the cloud to all your MQTT devices. And this is because the QS0 queue clients are stateless. So these queue clients reside in the MQTT connection process, or queue clients can also reside in the channel process. And normally they keep state to the queue server process, like either for flow control or for publisher confirms. And this is special, this queue type, because it's stateless. So it just fires and forgets the message. Whether it arrives, doesn't care. It also provides lower memory usage because we just skip the 1 million, classic queues. If you have 1 million MQTT clients that subscribe, we have lower end-to-end latency, again, because we skipped the classic queue process. And we have also lower publisher confirm latency. Now, there is a downside with this approach because there's no flow control. We must, if the subscribing MQTT client doesn't consume the messages fast enough, we must aggressively drop messages. So there's a default threshold, I think it's set to 200 right now, but it's configurable. And if the Erlang process mailbox is larger than that threshold and TCP buffers are full, which means you have TCP back pressure, the subscriber doesn't consume fast enough, then the messages are just dropped. And that's okay because those are at most once messages. And if you think about it, it's a bit similar to queue length limits, right? In other queue types that you have in classic queues or quorum queues. At some point, you need to either to reject those messages to publishers or drop them. So it's just a special, performance optimization for a very specific use case where MQTT clients connect with clean session 1 and quality or subscribe with quality of service 0. For all the other cases, we still use real queues. yeah, some people were already asking whether we can have this queue type for other protocols, AMQP 091. Maybe in the future. For now, we left it. We also wanted to first see how it performs with MQTT. Right, so let's talk about MQTT 5. So there are a few different protocol versions of MQTT, and MQTT 5 was released 4 years ago, and now it ships in RabbitMQ 3.13, so later this year. So there's no single big killer feature in MQTT 5. So you might be wondering, what's the point of MQTT 5? What does it provide? It's just around 20 new features, 20 new small features, which all add their own value. So I wrote a blog post about every feature that we implemented, but we won't have time to cover them all. But just to give you a high-level idea of what features MQTT 5 provides. So for example, one feature is message expiry. A publisher can set an expiry interval in seconds. If the subscriber is offline and doesn't consume that message within that interval, the server must delete the message. And in RabbitMQ, the queues will delete the message. So it's very similar to just an expiration field that you already know from AMQP 091 basic content. There's not only message expiry, there's also session expiry. So an MQTT session can continue across a sequence of network connections. And the session lasts as long as the latest network connection plus the session expiry interval. Now, when the session expires, both client and server must delete any session state. And the session state in the server includes the messages that are, get routed for the subscribing client, that are being sent to the subscribing client, so that are in the queues, and the client subscriptions, so the bindings in RabbitMQ. Now, we already have a feature in RabbitMQ that's called QTTL. So by simply setting a QTTL, that's the same as the session expiry interval. If the MQTT subscriber doesn't reconnect and consume within that interval, we just delete the queue, and therefore all the messages, and therefore all the bindings. And that's how we delete the session state. So very simple. Just set a QTTL, that's it. Another feature of MQTT 5 is reason codes on all acknowledgement packets. And one good example, so there are many examples that we implemented. One good example is negative acknowledgements. So if a message cannot be routed to a queue because no queue binds with the correct binding key or topic filter, then the MQTT connection process will simply send back a pub-uck to the publisher with reason code no matching subscriber. So this didn't exist in MQTT version 3.1.1, so there were no negative ucks. And this is again very similar to the mandatory message property and the basic return handler in AMQP 091. Another feature is topic alias. So topic alias is a very simple feature, just an integer value that publishers send instead of a topic name. And that's very useful if you have topic names that are very long and that needs to be sent repetitively. So you just save a lot of network bytes in that case. And it works by the publisher sending a topic, so sport/tennis/player1, and then it also sets a topic alias. This defines this mapping. And then RabbitMQ will remember this mapping in the MQTT connection, so in the process state, because this is not part of the session state, so this doesn't need to be persisted. And from then on, whenever the publisher wants to send a message to that topic, it just leaves the topic empty, and instead just sets the simple topic alias 1 in this case. And this is the last feature which we will explore for MQTT 5, and it's user properties. So many MQTT packets can contain user properties, and those properties are not defined by the MQTT spec. So, for example, the publish packet can have user properties, and we translated to AMQP 091 basic message headers if the consumer is an AMQP 091 subscriber. And this example is a bit more complicated, so on purpose, it should just show you what's possible with RabbitMQ. So you can suddenly not only route messages based on topics, but also on headers or on MQTT user properties. So let's say if you send a message, the topic sport/tennis/player1, and you set user properties, so these are just key value pairs. One example would be location, Berlin. And you bind a headers exchange to a topic exchange, and RabbitMQ you can bind exchanges to exchanges as well. In this case, we bind with a hash sign, so we match all the topics. And then we bind a queue to the headers exchange with xmatch all location Berlin. Then this message is routed because the user properties are matching. So it ends up in the queue, and then again the topic gets translated. So sport.tennis.player1 to the AMQ 091 format. And the user properties are also translated to AMQP 091 basic message headers. So it should just show you what's feasible with RabbitMQ. All right, so this is the last slide. And this is some topics we are currently working on. So Loic currently works on Quick. So he wants to support, have HTTP3 support in Cowboy. And this allows for shorter connection establishments for MQTT over WebSockets. So as a first iteration, he uses the QuickNIF from EMQ. And then together with Carl, I work on Native MQTT 1.0. And yeah, that's very exciting because basically we apply the same from Native MQTT to, or everything what we learned from Native MQTT can also be applied to AMQP 1.0. Because right now, the AMQP 1.0 plugin and also the Stomp plugin, they still proxy all traffic via AMQP 091. And as you can imagine, once we remove this proxying, we will get much higher scalability and better performance for AMQP 1.0. Not only that, but we will also be able to support more features of AMQP 1.0 in the future, because we're not limited anymore by the 091 protocol. And yeah, we will also get more information about AMQP 1.0 later in the keynote from Alvaro. And then Ilya, who sits here, works on native Stomp, and we also try to ship this in 4.0 if possible. Because for Stomp, again, it's all about the use cases: open connection, send a single message, close the connection. So we don't need 20 Erlang processes for that for that thing, right? Yep, that's it. Thanks for listening.
Any questions? Yeah.
You showed a graph for the differences in memory usage between the previous and the new implementation. Do you have any information on how does that impact on the CPU, especially for high churn of clients connecting to Rabbit, for example?
I don't have a graph for you, but well, I can tell that CPU usage is definitely lower, simply because you have less overhead. So this also reflects a bit the throughput and latency measurements. But I don't have a concrete percentage answer, how much on CPU you save. Yeah.
But as MQTT is simpler, that is lighter and faster than the regular AMQP connection, handshake, and the impact that has on CPU, for example?
Yeah, I wouldn't say it's naturally it's necessarily faster and higher throughput. That's not the case, but it's simpler to implement. Yeah. And because the protocol is so simple, we have such a huge ecosystem. So many client libraries. AMQP 1.0 has a higher complexity, and therefore, I think, less implementation. So that's Azure Service Bus, ActiveMQ, RabbitMQ, but not that many others. Yeah, but I think performance-wise, the simplicity doesn't provide you better performance necessarily. Depends.
So connection churn can still be a problem even with the native MQTT implementation?
Yeah, so connection churn was always a problem in RabbitMQ, but that's more because of bindings and queues that the clients create. So normally when we talk about connection churn, what we mean is that clients connect, they declare queue, declare binding, and all these thingies are a synchronous transaction in amnesia. So every node in RabbitMQ needs to write it to the database in a transaction, confirm it back. So that's pretty slow. So this will improve also with Capri in the future, with the new metadata store. But I think you can really, connect quite a lot of clients to RabbitMQ. If you just talk purely about network connection, that should be fast. What has been slow is creating bindings or topic bindings in RabbitMQ, because every topic binding is, again, uses this topic tree data structure internally. So it does multiple inserts into the database, all in one transaction. So this is kind of slow. By slow, I mean you still can have probably a few hundreds of clients connecting at the same time per second to RabbitMQ creating bindings. But if you do it like thousands per clients, and it really results in a lot of database operations.